My dear people, so far we have only considered that there is no loss whatsoever in terms of the flow that is happening. Yeah, but in reality there is always some loss that's happening. There is loss. Look at the flow over here. The flow is happening over here, but then what is happening in this area? Do you see? There is a region of turbulence, which means that the flow is losing some energy. The energy is not getting conserved, is it not? Is it? And also look at this pipe over here. When the pipe is inserted like this, the flow is not very steady, which means that there is going to be some loss, and the loss is represented by the letter K. I have no idea why. They, if I were the one who was making it, I would just represent loss by the letter L. But I have no idea who decided loss is always represented by the letter K. Yeah. And look at this. There is some loss here. There is loss here. There is always loss. And also, this is when the flow is going from a region of smaller diameter to a larger diameter. But look at this, when the flow is going from a larger diameters to a smaller diameter, again, there is some turbulence that's being created. Yeah. Now, let me ask you something. If the pipe is going like this, yeah, if the flow, imagine the flow will just first hit, and then there will be a sort of a turbulence created, and then the water will start flowing up. So there is again some loss of energy over here. Do you see? So there are always some loss that is happening in the flow of liquids. Yeah. So if Bernoulli's equation does not take into consideration all these losses, can it be practically applied? Can it be practically useful? Yes, my dear people, yes. Yeah. If we can understand the losses that are happening, and if we can add it to our equation, then everything becomes simple. Let me show you what I mean. Look at this. All that I have done is, this is the Bernoulli's equation, and this is the head loss, the total head loss, all the losses that are happening because of the pipe's contraction, because of the contraction in the pipe, because of the pipe going because of the enlargement in the pipe, because of the pipe going at different angles. Imagine if a pipe is like this, it is first going to hit over here, create a turbulence, go up, create a turbulence over here, and then go. So it is going to create some loss of energy. So all that I'm doing is I'm just adding this particular head loss value. Yeah, usually in this first year, for you the total head loss will be given in your problem. Yeah, so that all that you have to do is, whenever you have the head loss, you have to add it to the equation. Is that okay, my dear people? Okay, shall we go and look at a problem rather than just talking about it? Yeah. Okay, let's go. Okay, so what do we have here? Yeah, here we have that there is a pipeline of diameter 15 centimeter. Okay, at an elevation of 100 meter at section 1. I've just drawn over here. So the diameter at section 1 is 15 centimeter. So we have to convert it into meter, and it is at an elevation of 100 meter. So it is at an elevation of 100 meter. This is Z1. Okay, and section 2 is at an elevation of 107 meter. So section 2 is at an elevation of 107 meters. So it means that water, when it's going to flow, it has got to flow up. Yeah, okay. And the diameter of pipe at section 2 is 30 centimeters. So the diameter is doubling. Do you see here it's 15, here it is 30. So the diameter is bigger here. So when a discharge of 50 liters per second, so we are given the discharge, yeah, 50 liters per second. So we have to convert it into meter cube per second. Okay, is passed through this pipeline. The pressure at section 1 is observed to be 30 kilopascals. The pressure is 30 kilopascal. So we have to convert it into pascals. Okay, and the total energy loss is 2 meter. Why do you think there is a energy loss that's happening, my dear people? Why do you think? Pause this video, think of it for a couple of seconds. Yeah, okay. So since the water is flowing up, it's losing some energy. That's the reason for the energy loss. Yeah, okay, we are asked to calculate what would be the velocity of flow in section 1 and 2. So C1, C2, and also we are asked to calculate what would be the pressure 2. These are the things that we have got to find out. So again, all that I'm doing is I'm just highlighting all the information that we are given, so I do not lose anything. Yeah, okay, now let's go. I've just redrawn the diagram here so that we do not lose any information. So look at this. The head loss, I've written it as capital H and L, head loss. Yeah, 2 meter. That's happening. Okay, now to find C1, C2 and P2. Okay, so from the continuity equation, yeah, we know the volumetric flow rate 1, the volumetric flow rate that's happening here equals to the volumetric flow rate happening over here, which is 50 liters per second. So how to convert the liters per second into meter cube per second? All that we have to do is divided by 1000. So 50 divided by 1000 is the volumetric flow rate, 0.05 meters cube per second. Yeah, well, there is also a head loss. Yeah, so be quite careful about this. Okay, now all that I'm going to do, my dear people, is I'm going to use the volumetric flow rate. V dot equals C times A, or A times C. So C equals volumetric flow rate divided by area 1. So we know the volumetric flow rate is 0.05 meters cube per second divided by the area. Here we are given the diameter 15 centimeter. So it is a circular cross section. Area of a circle is pi r square or pi d square by 4. That is what I've used here. Pi by 4 times d square. D square is 0.15 square. Why is it 0.15 square and not 15 square? Huh? Oh, come on. Please don't let me catch you on this. Yeah, exactly. Because it's centimeter here and I've converted it into meters. Always, always, always use the standard form, my dear people. Yeah. So when we put this in the calculator, I get the velocity to be 2.83 meters per second. Now, people, think of this. Okay, the velocity 1 is 2.8 meters per second. And this is a smaller cross-sectional area. Yeah, and the water is also flowing up, so it's losing some energy as well. Now, what do you think is going to be the velocity at section 2? Do you think, don't look at what is over there, okay? Do you think it's going to be greater than 2.83 or less than 2.83? Increasing diameter and also water is going up. What do you say? What? Exactly. No, I cannot hear what Liam just said. Liam, what? I see, exactly. He's correct. Yeah, he's correct. It is going to be smaller. Let us check it. Okay. So C2 equals, I've just used the same thing, V dot 2 by A2. Volumetric flow rate is the same, 0.05 divided by pi by 4 into 0.3 square. 0.3, it's because of the the diameter 30 centimeter being made into meter. So I get this particular value.
So now to find P2, I'm going to be using Bernoulli's equation. Yeah. So P1 by rho g plus, which is the pressure, the pressure head, the kinetic head, and the datum head, is equal to the pressure head, kinetic head, and the datum head on both the sides. But we know that there is loss. So I've added it over here, plus the head loss. Do you see, people? This is the Bernoulli's equation, but since there is loss, usually we assume that there are no losses, yeah? But since we are assuming, since we are given that there is loss, I've just added it over here. And we know P1, we know density of water, we know what is C1, we just found it, we know gravity, we know Z1, 100 meter. Similarly, we know rho, C, and Z2, and also HL. The only unknown is P2. Yeah, all that we have to do is just substitute everything that we know in the equation. That's it. It is as simple as this. Yeah. And then if we rearrange the equation, I get the pressure to be minus 54.37 kilopascal. Why am I getting it in a negative value? Ooh, why do you think I'm getting it in a negative value? I have no idea why I made this noise. Okay. Okay, guys, I want you to tell me why this is a negative value. Okay, do you think I've actually made a mistake, or do you think the pressure itself is negative? Yeah. Okay. Let me know about this during the tutorial. Okay, I'm really looking forward to hearing your answers.